Afternoon, everyone. Thanks for sticking around till the end here. And also thank you to Compressor Tech 2 for having me and for accommodating the schedule swap. So I'm the reason it's me, I'm the problem, as Taylor Swift would say. So the program was a little out of whack. I was supposed to speak in the morning, so thank you for accommodating that. So these remarks really come to you as a former operator. I worked for Kinder Morgan, as Jack mentioned, and I put together these slides last year and spoke at a couple different conferences about our thoughts at the time, coming from Kinder Morgan's perspective, on blended hydrogen into natural gas pipelines. So I'm putting that hat back on, even though I don't work for them anymore. I'm probably not a very good salesperson in that sense, but I'll try to blend in a little on the centrifugal side too, which is mainly what we make now. This focus, or a lot of the focus at the conference, has been a little heavy on the reciprocating compressor side, as it should be, because they serve a very good part for the hydrogen market. But there is some needs for centrifugal compressors when you have the higher volume flow. And for that matter, I think these slides will come in handy talking about the challenges with hydrogen on centrifugal compressors. So with that, I'll go ahead and get started. Let's see. Yes. Okay, so hydrogen in natural gas, blended pipelines in North America, or at least the US, pretty tempting, right? We have a superior backbone for development. We have a ton of natural gas infrastructure, pipelines that connect up to gas-fired power and combined cycle power plants that are some of the low-hanging fruit. You know, big over 100 megawatt power plants, 500, 800 megawatt power plants in this country, and there's a lot of emissions in those in that one plant. So when it comes to thinking about hydrogen, it makes sense to kind of think, oh, well, why can't we just blend it in? But a lot of these slides are going to kind of paint the picture that maybe that's not so easy, and that's the perspective I want to give you today. Now, the other thing that's been pointed out throughout this conference is that green hydrogen really has a different, the pipelines and the machinery don't care, but when it comes to how you use green hydrogen, it's going to be very different, right? A lot of starts and stops. It's using curtailed green energy, so ideally it would be curtailed energy that you can't put into the grid from your wind, your solar power, and you're then using that curtailed energy to make hydrogen. So that's a lot different model than how you would have a continuous blue hydrogen production that's using something like natural gas via steam methane reforming to produce hydrogen in a continuous way that continuously feeds into a user that might want to blend into hydrogen on their gas turbine for power. So when it comes to pure hydrogen lines, that's your alternative instead of having blended lines. And when you come out and you want to build a pure hydrogen line for maybe someone that wants to blend at the point of use or in a hydrogen hub, you could optimize the size of these lines, and you could also make them shorter and purpose-built in terms of the material selection on the steel. With blended natural gas and hydrogen lines, you basically are using our aging infrastructure already. So the problem there is a lot of our infrastructure was put in many decades ago. So different steel compositions by decade, different corrosion over the years, hard to get a handle on that. And that's kind of where I'm going with being a more negative on blended into the pipeline infrastructure. So we've already talked a lot about cost for hydrogen, and basically blue hydrogen being a lot lower cost to make than green hydrogen. DOE did put out goals wanting to establish $1 per kilogram in 2030 for blue hydrogen and $2 per kilogram for green hydrogen in 2030. One thing that's not discussed is using nuclear power to make hydrogen, and that's regarded as pink hydrogen. The costs there are a little less known, but I think that's also a very viable solution, especially when you start talking about some of these hydrogen hubs and getting away from the carbon sequestration requirements. So one way to incentivize that DOE goal is to come out with a tax credit, as we talked about. So the Inflation Reduction Act made this really easy. and they accomplished their goal by not doing technology development, but basically just giving us the tax credit. But this does help propel the market, and that's a good thing for right now, as long as those tax credits don't go away. The interesting thing is, if this slide basically is directly from the Inflation Reduction Act, they give a credit in dollars per kilogram based on how much CO2 is produced in the production of hydrogen. So with more CO2 produced, you get less of a credit. But it also means that if you can get your blue hydrogen to qualify by capturing that CO2 and reducing the CO2 production in the production of blue hydrogen, you also get a tax credit for blue hydrogen. So those guys also benefit from this, which is pretty nice and something to note. So it's propelling a lot of innovation on the blue hydrogen side as well. So this is kind of a fun thing to look at, and something I just put in here because I was thinking about how technology takes shape. I worked in R&D for 10 years, and a lot of things take time. So you can look at some of these curves and they're kind of hard to see, but on the right side, a lot of recent developments in the last 20 years, like the iPhone or computers or the internet or even TV, sort of had this immediate curve up. So immediate uptick, basically. And that was basically because there wasn't a lot of competing technologies out there when these things came out. But you can take something else, for instance, the washing machine was invented a little bit, I think, before 1930, and it took a good 30 years to even get to 50% usage of the washing machine. And that was because we had another way to do it, right? We could just hand wash. So, 30 years sounds like a really long time. We're talking about trying to get hydrogen going in maybe 5 years, but we have to remember hydrogen competes with other technologies. We have natural gas that provides power. We also have ammonia and methanol as competing technologies for low carbon. So those are also kind of trying to gain market acceptance, and it will be, in some ways a competition. Bottom line is, technology adoption curves very much depend on the technology themselves. So you have to look at that when you're trying to think how fast is this going to take shape. As a cost analogy on why is hydrogen so expensive and when are the costs going to come down? I heard the question and I thought it was a good question about why does everything have to be API 618 or 617 on the centrifugal side? And I do think OEMs take exception where they can to try to reduce costs, but the other way you can do it is through standardization and simplification. And we can't do that right now because it's a moving target. We don't know how many of these hydrogen units that we can make identically, but at some point that standardization will help to reduce cost. So on the LNG side, I made this chart when I worked for Apache, and we were forecasting how LNG prices were kind of going super crazy in around 2012, 2013 timeframe. So historically, they had averaged, well below $1,000 per ton. And then a lot of LNG plants were coming online in Australia, and there were multiple different problems in the market with inflation and also Australia labor cost. And a lot of these plants did go into Australia, but you could see how the cost went up. Well, that was the forecast at the time, and it wasn't just me. A lot of people were putting that out and saying LNG is getting too expensive. And then these same plants are on this same chart here, so they kind of came in close to those numbers, well above $1,000 per ton. But then this happened in the last 10 years in LNG. And that's simply driven by standardization, simplification, taking advantage of sites, and economies of scale. So a lot of these sites in Louisiana and the Gulf Coast were able to take advantage of some of those labor markets and standardization. So that's something else to keep in mind with hydrogen and making that analogy. Another thing is costs come from technology development, or cost reduction. These are other ways that the refining industry, Elliott goes to all these different refining conferences, and I'm trying to learn about the downstream markets that I didn't know about before, but they're looking at different ways to get to hydrogen. So it's not just steam methane reforming, which is this top line, but these are other possible ways where you can make hydrogen out of natural gas. Some with, well, varying levels of carbon intensity. Steam methane reforming produces the most and is also endothermic, so it requires energy. But some of these others don't require energy. They release heat, which means you don't have to burn fossil fuels to get the reaction started. Water through electrolysis is also an interesting one, needs energy, but we've heard today other means like pyrolysis that also accomplish the same goal without carbon emissions. Another innovation is being able to produce the green energy at higher pressures. So if an electrolysis process can output that green hydrogen at higher delivery pressures, that takes that inlet pressure burden off of the compressor, right? We don't have as much pressure ratio to do on the compressor side if we're being given a higher suction pressure. So another chart I like to point out is, just thinking about the different ways that hydrogen is going to be produced and used is really the storage form and what I was just mentioning, the compression profile. So depending on what pressure it's delivered at, basically sets your inlet compressor or booster compressor into whatever you're trying to deliver into. Maybe it's a hydrogen pipeline. But it's also important to think about which storage mediums can accomplish these goals. With blue hydrogen, we already have natural gas storage and we have natural gas pipelines that have line pack in this country. So in a way, your storage is built into the natural gas having the energy right there. Whereas green hydrogen, you need to convert to make hydrogen, and it's only through certain times of the day when you have that excess energy through renewables. So green hydrogen really needs the storage more so than anything else. And it might not be in the form of hydrogen. It could be ammonia, and well, methanol is kind of a different way, but liquid hydrogen, another viable, and hydrogen line pack. If we start building pure hydrogen lines, we can utilize the line pack in those lines. So this is the way that we produce natural gas right now. We have production and a lot of pipelines that deliver into pipeline or power plants and GCCs. What we're talking about with blending is basically taking this same natural gas and using it in some kind of reforming process to produce blue hydrogen. And then what would be nice is to be able to offer that blending station right at the inlet of those power plants instead of trying to blend hydrogen into all of the pipelines in the US system. So basically a purpose-built line right there at the entrance of the plant that would also act as the blending station. And then, of course, we would need CO2 pipelines to follow from any kind of steam methane reforming process. But hopefully with a hydrogen hub, you also have the ability to accommodate green hydrogen and pink hydrogen and feed into that same maybe pure hydrogen network that you build up as a result of maybe blue hydrogen kind of taking the leading step. So that's sort of the concept for being able to blend and offer blending stations, but doing it without using the aging infrastructure in the US. It's also true that hydrogen hubs, or at least areas where green hydrogen is likely to come about, are probably favored where solar and wind are more concentrated. That favors lower green hydrogen costs. So we need to think about delivering green hydrogen to the areas that don't have the low cost. And that's why it might start to make sense to also look at things like ammonia, where we have to go across the ocean. Okay, so now we get to talk about compressors. When we start talking about hydrogen, I like to think about Jaws. So you're gonna need a bigger boat. Everything gets bigger. Recips struggle with the volume flow in certain areas, right? So they need more cylinders, bigger cylinders, block mounted, not skid mounted. You start to go down that road. With centrifugals, we're okay with volume flow. We love flow. We struggle with head. And I'm going to show you why and then what we're doing to counter that. So this is the only equation, I promise. This is your isentropic compressor relationship. So your pressure for your compressor, discharge over suction, is produced by this equation. With hydrogen, your specific heat, basically your CP, is basically 14 times that of, or 7 times that of natural gas. So your specific heat with hydrogen being so large, basically messes up this equation and puts a very large number in the denominator. So to keep this same pressure ratio, we have to do something in our design of a centrifugal compressor, which would be this Euler equation on the right side. So we can either play with speed or diameter or basically velocity. Those are our options as a centrifugal compressor manufacturer. So right now, we've accomplished that by adding more stages, more impellers, to accomplish the same pressure ratio that we would do with natural gas. What we'd like to do, ideally, is go to either larger diameter or more speed, but the larger diameter is limited by a lot of rotor dynamic issues. So a lot of us, centrifugal compressor manufacturers at large, are looking at the speed in the R&D section. You know, how can we make impellers differently to go a lot faster? And that would help us to not have that same really high impeller count required. So when it comes to hydrogen, we've touched on all this, and I don't want to go into too much detail since I don't want to be repetitious, but I will mention, you know, for us on the centrifugal compressor side, the dry gas seals do require a little bit more specialized seal design, but when you start talking about 30,000 RPM or 50,000 RPM, much higher speeds, this is even a bigger challenge for the dry gas seals as well. So that's where some additional innovation and R&D is required. Now, dry gas seals for normal hydrogen compressor speeds at 15,000 RPM, a lot of us can do that today. So you do have that in your hip pocket. The other thing is hydrogen embrittlement, which tends to be more of an issue on, as I mentioned earlier, operating close to, or the MAOP being really close to your steel strength, yield strength. And I'm going to show you a couple charts on why that's more of an issue with pipelines than it is with you know, what we do on the impellers, which are basically stainless steel parts. And then, of course, obviously the safety issues and some of the volume handling issues, because you need so much more volume to make up that same BTU. So the gentleman from Caterpillar had a really good chart that also kind of made the same point for an engine. And I think Jacob was also talking about it. And he was also talking about the methane slip that was sort of entering into some of the emissions calculations. This is for a turbine, so this is different, and it doesn't have the same methane slip issues. But just as an example, this is a 50 megawatt for isopower for an LM6000, and it's the fuel flow to that turbine. So this is your percentage of hydrogen on the bottom axis and how much volume flow you need. When you basically start out, you're blending in certain amounts of hydrogen, and your natural gas, which is this orange line, is tailing off as you introduce more hydrogen. But it's not a one-for-one trade-off, right? And that's because as you introduce more hydrogen, you still have to make up the BTUs in volume flow, and that's made up with the natural gas. So the natural gas doesn't come off as quickly. And that's why your emissions aren't going down as quickly. So for instance, when you get to 50% hydrogen, your natural gas has come from 7,500 standard cubic feet per minute to around 5,000. So you've cut your natural gas fuel flow by about a third, but you're at 50% hydrogen. So you haven't reduced your natural gas by 50% just by being at a 50% blend. And that's why your overall mixed gas fuel flow goes up, because you're having to add more natural gas to make up for the BTUs you're missing on the hydrogen. This is all to say, it's really important to get to high amounts of hydrogen to start making a big difference on emissions. When you're down here at 10 or even 20% hydrogen, you're not making enough of a difference because it's 1/3 of that on your CO2 emissions that you're actually gaining. So this is another point where, you know, blending 50% or more is really going to get you those appreciable differences that you need. So basically, that same analogy works on the engine side as well. His numbers were slightly different because methane slippage is helped by the hydrogen. So that's why his numbers, I think, were a little bit different. So hydrogen transport in a pipeline, at least pure hydrogen lines or blended, you need about 10 times the head increase on centrifugals So your power and speed have to increase for typical pipeline ratios. You're going to do this with multiple impellers right now until you get those speeds up there for centrifugals. And you also need an additional flow increase because you're delivering, you're trying to keep your BTUs delivered the same to wherever your turbine or engine is that's burning the fuel for power. You also have the hydrogen embrittlement issues, whoops, sorry, and the leakage of the very low density gas. The speed of sound here, it's about 3 times higher in hydrogen, and with centrifugal compressors, that actually helps you because you don't start to have Mach number issues when you're over to the far right side of the compressor map. With reciprocating compressors, it's really only an issue with your pulsation bottles maybe needing to be redesigned because they were designed for your natural gas speed of sound, and now you have 3 times the speed of sound in hydrogen. But there are ways to get around that, as they've mentioned earlier. So the other thing is there's a lot of other sources of venting at a compressor station. It's not just your compressor. You have a lot of threaded fittings, you have regulators, you have valves that possibly leak, you have the metering and GC stations, as Jacob was mentioning. So all of this adds up to, it makes a lot more sense to build purpose-built hydrogen pipelines and stations rather than blending into existing stations because there's so many retrofits that have to go on using existing equipment. Now for just a little bit more on centrifugals. As you add more hydrogen, and like I said, you really want to be above 50% hydrogen to start talking about, 10, 20% curbing of the CO2 emissions. But your centrifugal map starts to get a little bit more complex. So, typical flow versus head map, you're right here in the sweet spot for your maybe typical pipeline compressor. When you add a little bit of hydrogen, maybe you stay on the map, maybe you re-wheel to, if you get up to 20% hydrogen, maybe this is all doable. But once you're out here at 40 or 50% hydrogen, you're beyond the limits of that machine. So you're replacing the entire compressor. Or maybe you're feeding into another compressor in series. It's just not possible to re-wheel and hit these points. So this is another really good point about favoring purpose-built hydrogen. So this is just an idea, to give you an idea of how things start to look as you add more stages, more impellers to get over that high head issue. So this is your isentropic work versus the hydrogen content. And, a typical pipeline compressor could probably handle, like we said, maybe even, this is showing up to 30% with a good re-wheel study in your existing driver, or, you add, extra power to get up there. But once you start to add, these higher hydrogen contents, you start to get things that don't look like a typical pipeline compressor. So this is a single body process compressor that's a barrel style. So it's kind of made for hydrogen and it works in refineries right now. This out here is a hydrogen machine that we've done and others can do the same. But it has, basically 3 separate casings. And this is 4 smaller casings for a smaller volume flow arranged around an external gear. But the idea here is, you need a lot of impellers. So you're limited to probably 10 or 12 impellers per casing. So you need maybe 40 impellers, so that's 4 casings. That's why things don't look like your old pipeline compressor when you go into hydrogen. Now this chart might be, I definitely took it from a previous presentation that we did, and I think it's a little too negative. But this shows you, where they think recip compressors should be, flow versus head. And recip compressors can do a lot of head. That's not a problem for them at all. They can handle a lot of pressure ratio. They're limited on volume flow, and I don't really think they're this bad on volume flow either. So that's why I think they're a little negative on this chart. But also notice centrifugals, yeah, we can handle a lot with a multi-stage, multi-barrel centrifugal on the flow, but we can't hardly handle any head. So, a typical gas pipeline station's down here, hydrogen for a small pressure ratio is about right here. And we need to be here, 3.5 to 5 on some of these booster compressors on the pressure ratio. So that's why, some innovation and R&D is necessary. And I think all of us as compressor manufacturers are working actively on the R&D front. Okay, so this is just again, making the point about, why I'm pretty negative about blending hydrogen into the US natural gas infrastructure. Basically, different studies that are out there, and a lot of them are coming out of Europe because they've put a lot more into university or at least public domain, looking at hydrogen effects on mechanical degradation of carbon steels. And what you start to see is the effects are dissimilar as you add hydrogen, which is the x-axis. Different steels in this study had very different responses. So much that, the material strength would drop off dramatically. Some of it was more linear. Some of it hung in there and then really only dropped off towards the end of the high hydrogen content. And they were talking in a lot of these studies, and the references are here for you, about a lot of different forms of degradation. Hydrogen embrittlement decohesion and hydrogen embrittlement local plasticity. The good news is, through all these studies, they were getting to where they could easily predict the effects based on steel composition. And they could even engineer the right type of steel that was more immune to hydrogen. But it's a little scary to think, if you don't know what the steel is, and you don't know how much corrosion is going on, what's going to happen. So this is our installed natural gas transmission lines by decade in the US. And this is basically, it's a confusing chart, but we're right here on the right side. So this is the present day in the calendar year. And these little bars show you when we installed different, how much, footage was installed or miles by decade. And you can see there was a huge amount of US infrastructure that was installed in the 50s and 60s. Like, they installed 70,000 miles in the 60s and 70s in that decade. And then you come down here into the current decade, and we've done like 30,000 miles for recent decades up, to 2019 is in yellow here. So there's a lot of aging infrastructure. And yes, it's underutilized, which is advantageous, but we don't know exactly the state of all of that. And I think a lot of pipeline companies are working on that. That's why the testing that Jacob said was required if you're going to put it into, existing pipeline steel. Okay, so I'm going over, so I'm going to go really fast at the end here. So we had two really quick case studies, and I won't go through those in a lot of detail, but they are in here for your notes. This one was a lower pressure or a higher pressure ratio, lower flow, and it just compares what different recip compressor vendors could do and how they kind of design their compressors. And the second one was higher flow and less pressure ratio. So that was kind of neat too. And it gives you just, how many units are required. Overall horsepower ends up being the same, but combination of high speed and low speed, combination of block or skid mounted. And then this is that same embodiment, so it's there for you, the different ways that we can accomplish this with centrifugal compressors. When you start getting up at higher flows, you start needing to do something with a double-ended motor that can do basically in this 2 different casings, or a string that has 2 different casings. And then this is for your notes. This is a general summary of all the different possible ways to compress hydrogen. It also has on here integrally geared compressors, and I know there's some manufacturers here today that make IGCCs, so that's another option for you, and this gives you advantages and disadvantages of those. Okay, so final slide. Thanks for bearing with me. I'm pro-hydrogen, very much so, but I'm negative on blending into US pipeline infrastructure. Basically because I think we need to be at higher levels of hydrogen, and I don't think we should do that with existing infrastructure. We also know that compressors are going to require a lot of different changes, and it's possible to design really well if we have a clean slate to do pure hydrogen lines with pure hydrogen compressors. Okay, so I'm sorry I went over, but thank you all so much.
Thank you very much.